Okay.
Assalamu alaikum. Bismillahirrahmanirrahim. Rabbi shrali sadri wa yassirli amri wahlul uqdatam min lisani yafqahu qawli. Rabbi zidni ilma. Okay, today we are going to discuss one more chapter for a quick revision, and that is chapter number 3, hardware. This is a lengthy chapter, but let's see. Let's go do it very quickly. What we need to study here is the computer architecture and what are included. Again, very brief discussion of that will be done today. Then input and output devices, then data storage, and lastly, it is going to be network hardware. So the same chapter as you have studied, spanned over a number of pages, is going to be started from here. First thing is computer architecture. In this, we need to know what is CPU. So let's link it with real life. We humans also have CPU, and our CPU is our brain. So just whenever you are studying the term CPU or any component of CPU, just link it with real human body's CPU or the brain. It has the responsibility for execution and processing of all instructions. Like you may have heard people say that the person is brain dead. A brain dead means a person is alive, he is breathing, but still we call him brain dead because he is not able to process, he's not able to do anything. So it means CPU or brain is the integral component of the computer system or the human body. Fine. It is consisting of control unit, ALU, arithmetic and logic unit, and registers and buses. So first of all, we talk about what is a microprocessor. A question can come in the paper, maybe a mark, asking you that what is a microprocessor. So it's an integrated circuit or a microchip that is going to be, either we call it a processor, CPU, or microprocessor. These all are the alternate words, and they all are talking about a system that is composed of ALU, CU, and registers. Okay? And definitely the buses are there. CPU is containing the system clock, and it is also containing the primary memory. Should not be very clear. It is not containing, or actually it is not a part of the CPU. But since CPU and memory are constantly linking with each other, that's why they say that CPU is also containing the primary memory, because primary memory actually means, I hope that you know, RAM and ROM. But here we are referring to the term RAM in order to work on primary memory. Any questions till now? CPU itself is clear, microprocessor, CPU or processor clear, linking it with real life, real human body's brain. What is von Neumann architecture? Before the introduction of von Neumann architecture, what was happening? Everything was hardwired. Like there was no concept of program. So von Neumann was the person who said that there should be a program that will be there, and people should be relieved to carry on their tasks, and the program will be there to take care of the human's work. And he proposed the idea. And that was done somewhere in the mid 1940s. So before the introduction of this von Neumann model, everything was just done by the people then and there. Every instruction was written and people were doing it just then and there. So he proposed the concept of a CPU, or you can say processor. The processor will be able to access the memory. The way we talk about our human body also has something similar. Memories are able to store programs as well as data. Now, be clear, programs are like Adobe Photoshop is a program, just giving an idea. Python is a program. So this is a program. And when you are writing something in that program, then that means data. Stored programs are made up of instructions which could be executed in a sequential order. Or in other words, actually, this is the definition of a program. Programs are basically made of instructions, and these instructions are going to be followed one after the other, executed one after the other in a sequential order. And since you have done programming, you have done pseudocode writing, that's why that should be making some sense to you. I think that is not a problem for you. Any questions? Any questions?
So far it's good.
Okay. Now moving to summary, like that is, since it is a revision guide, that is why it is simply composed of the summary components, and this is what the CPU is composed of. First thing is the ALU, Arithmetic and Logic Unit. It is there to perform arithmetic operations as well as logic operations. So you can see arithmetic is just plus minus, and logic operations are and or etc. And this is one important thing that we need to know. Computer may have more than one ALU, and that is we talk about as a core. And ALU is allowing multiplication and division using shifting operations. So from this, we are just recalling that what we have learned the shifting in chapter number 1. Logical shift left and logical shift right. So we have learned in chapter number 1 that when we perform shifting to the left, that means multiplication, and shifting to the right results in division. I hope that that is what we clear. We are clear about. So same is ALU is doing multiplication and division, but that is performed using the shifting operation. Now ALU's function is very clear: plus, minus, and logical operations using and or, and then multiplication and division by us performed using a logical shift left or logical shift right. Second component is my control unit. And what is control unit doing? It's reading instructions from the memory. See, just think from ourselves. When we talk about us, we have some instructions stored in the memory. And those instructions are processed by the computer processor, but CU or control unit is there to read the instructions one by one from the memory, understanding what is supposed to be done, and then it is going to execute. So here we can see signals are generated during the fetch, decode, execute cycle that is coming just after this topic to control all the components of the computer. So actually CU, as the name suggests, is controlling all the operations that are happening in the computer and is dealing with fetch, decode, execute cycle. Fetch, decode what to do, and execute accordingly. And this keeps on happening with us too. Like we are having this happening all the time without knowing. Unknowingly, this is happening with us all the time. Fetching the instruction, decoding what to do, and then executing it. Control unit is doing the synchronization. Okay, now there are a few points that I really want you people to remember, and that is the synchronization. And what is synchronization? Just keeping a track of everything happening smoothly and program instructions throughout the computer system. So control units, basic job that you need to know that can come in the paper and that has been coming in the paper is the process, is the task performed by CU. So control unit is synchronizing data flow and programs instructions throughout the computer system. That will be definitely giving you 1 out of 1 at least. So, okay, fine.
Yeah.
This is the definition that you need to know for control unit. Or CU, it is synchronizing or just keeping a track that everything is running smoothly. Like synchronization is a term that we use quite often. So synchronization of data flow and program instructions. Whenever the program instruction is going to be needing the data or what is happening. So this all is handled by the CU. Now, after that, registers. Registers can be general purpose or special purpose. And what are they? Again, a definition can come in the paper, has come in the paper. High-speed areas of the memory within a processor. That is the simplest of all definitions. Registers are simply high-speed areas of the memory location within a CPU, or you can say used to store small amounts of data. Again, remember, memories are not very huge for register. They're simply storing very small data, and that data is needed to be processed at that time. Like talking about us, like just giving an example, not and registers are the fastest. A question can come in the paper talking about the speed. So registers are the fastest. Then it comes to RAM, or you can say cache. Cache is the next fastest. Then second on the third on the third place, it's the RAM. So this is the sequence of all the operation wise the speed of the different memory components. And it is going to hold the data, it is going to either hold, or it is going to hold the address of the next instruction. So we are going to talk about these also, like CIR, MAR, MDR, ACC, the 5 registers that we need to know, that PC, CIR, MAR, MDR, and ACC. So these are the 5 registers that we need to know, and their operation and what are they doing in a sequence also. So is the definition of register clear?
Yeah.
Registers are high-speed memory locations inside the CPU or inside the microprocessor, and they are there to store the small amount of data, or they are there to store the small amount of addresses. That is going to maybe giving you 2 out of 2. If the question is of 2 marks, then you can write down these 2 points to gain decent 2 marks. Another important component of my processor is system clock. Just like the clock, what is clock doing? Like right now, it's maybe 5 o'clock. So I know that's 5 o'clock. After 10 minutes, it will be 5:10. Similarly, system clock is doing somewhat similar. It is producing the timing signals. And these timing signals are there to ensure smooth functioning of the microprocessor. See, microprocessor is not doing one task, it is doing multiple tasks, multitasking. And for that, it needs to know that when first job is completed and is the turn of the second task. Second task job is complete. Now is the turn of the third task. So this is synchronization. Now, whenever first task time is over, then immediately the shifting of the processor's time towards the second task. Second task time is over. Now it is shifting to the third task. So this is what is handled by the system clock. And CU and system clock work together to perform this activity. So there is a smooth functioning of all the processes, and all the processes are getting equal time share. No one is superior, no one is inferior. They all are handled equally. And now one more thing that we need to know is, now system clock is used to produce timing signals on the control bus to ensure all functions are synchronized. So this is going to be a very efficient definition, I should say, a very decent definition to again give you 1 or 2 marks that if they are coming in the paper. So this is again important. You can note down this definition for yourself, and that is going to help you a lot. Now, talking about the changing the clock speed, by default, there's a clock speed that is for that purpose, for that computer system or microprocessor. But we may change the speed, and that causes overclocking. And in extreme cases with overclocking, what may happen? Your system can lead to overheating, and your system may crash also. Because think for yourself. For example, if I say right now we are here, fine. Assume that we are going to keep on studying and studying and studying, and a time may come that you say, Miss, we can't study at all. I mean, we are that is going beyond our understanding. So that results in overclocking or overheating. You will say, I can't understand. So similarly, when you are trying to make your clock speed, you're going to change the clock speed. You are going to make it work beyond its capacity. Like its FDE cycles are changed by using some mechanism. So that may result in overclocking, and that might result in your system crashing completely. Then we have to talk about the buses. And what are buses? Simple. Buses are the wires. And these wires are either to transfer the data, or they are there to transfer the addresses, or they are there to transfer the control signals. With respect to this, one more important thing about the buses are their parallel data. So if a question comes in the paper from chapter number 2, we talked about the parallel transmission and the serial transmission. So with parallel transmission, that you can even mention the buses. Okay. And the parallel transfer means faster transmission, and the width of the bus can vary also. Like you can use an architecture that is based on maybe 16-bit buses, or maybe 24-bit buses, or maybe 32-bit buses, or 64-bit buses. So the amount of data that can travel can change through increasing the number of bits that can be transmitted at a time through the buses. So if you're using a 64-bit bus, it means definitely it will be carrying 8 bytes of data at the same time. So this is just a revision that we have talked about buses. Buses are wires that are there to transfer data, addresses, or controlled signals. And here we can see address bus is unidirectional, carries addresses throughout the system. Data bus, as the name implies, is bidirectional, is carrying the data. And this data is carried to and from CPU memory and from the input output device, from the input devices to the output devices. So this is the complete description of the data bus. Bidirectional is allowing the movement of data throughout the whole system, from or to CPU and memory, and to and from the input and output devices. And thirdly, control bus is bidirectional, but its size is limited to 8 bits only. We can increase the bit width of the address bus and the data bus, but the control bus width is 8 bits only. It does not go beyond 8 bits. So bidirectional carries signals from the control unit to all the computer components. As you can see, the need of control bus is to carry the signals throughout the whole system, throughout the whole computer system. And lastly, the width. This is what I talked about. If I am using a 64-bit bus, and if there is another system that is using 24 bits bus, so which one do you think is going to be working faster? 24-bit bus computer system or 64-bit bus computer system? Which one will be working faster? Yes, what do you think?
Like the 24-bit one?
24-bit will be working faster, 64 bits will be working faster.
I know, 64.
Definitely. So this is what we need to be very clear about. Okay. So any
Yeah.
question can come in the paper. You should just be very clear about the 64 bits means it can be addressing 8 bytes of memory location. Definitely 8 bytes, and another one is 32 bits. So definitely 4 bytes and 32 bytes. 32 bits, 64 bits means it's nearly the double. So this is what we need to be very careful about. A question from this topic can come in different styles. We should be very clear about. And I think a lot of questions are there which you have solved also from this, and they are a bit tricky also at times. So be very clear. FDE cycles, what are the components that are helpful, the increasing the size of the buses. And remember one important thing, we only increase the size of address bus and data bus. Control bus is fixed at 8 bits. We never increase the size of the control bus. Okay? Width of the address bus and data bus is determining the word length and the performance of the computers. The same thing as I talked about is mentioned here also. So I hope that this topic is clear till this point, isn't it?
Yeah.
So RAM, by the way, another word for RAM is IAS. So if they use the word IAS, do not get confused. IAS is an alternate for the word RAM. So either we say RAM or if they write IS, still they mean the same. Because again, RAM is accessed immediately. Whatever is held in RAM, that is the primary memory. And we know that even with us humans also, if we have certain things in the copy, and when we are preparing for the exam, all the material in the book or the copy is taken in the memory. And then you go for the examination. Similarly, same case goes here. All data being used in the programs need to be transferred to RAM. This is very important. If you have certain things in your hard drive, if you have anything in the computer systems that needs to be transferred to the RAM, memory is made up of an address and its contents. The address identifies the location and the instruction, location of data and instructions. So your data and instructions are what you need to do. What you need to do. Like for example, am I supposed to store the data? Am I supposed to add some component to the ACC? Am I supposed to fetch some instruction from anywhere? These are all the instructions. And the data is, for example, maybe 5. 5 is the data. All memory locations are unique, remember. Memory locations are always unique with us also. Allah Ta'ala has blessed us with memory, and this all memory locations are unique. No memory location is ever going to be overlapping. Primary memory includes read-only memory, which cannot be altered. ROM contains startup routines for the computer. So another topic of this chapter is going to talk about this once again. And this topic of startup routines and BIOS, etc., will be covered in chapter number 4 also. But here, just a description because of memory. We say RAM and ROM. So they have talked about RAM first, IAS, and ROM also, which is storing the permanent non-volatile voting instructions. Okay, that the thing that is needed to at the startup of the computer system. So any questions?
No.
Okay, fetch decode, very interesting. So in order to perform this fetch decode, like see, again, talking about us also, the way I said, we fetch the instruction first, we decode, like you are given a question paper. So first of all, you read the question, that is fetching. You understand what is the requirement, that is decoding. And then you start answering the question, that is executing. And once you are done with one part or one question, then you move to the next. Exactly the same thing happens in the computer. The CPU is first of all fetching the data and instructions, what to do and where to do on from the memory and stores them in the appropriate registers. Both the address bus and data bus are used in the process. Each instruction needs to be decoded and finally executed. This forms the fetch decode execute cycle. The way when we are solving a question paper, that is assume this as fetch decode execute also. Now this is understood very well if you just pay attention to this whole process. So here in our book, they are representing the same in the form of let me open the should I open the book or is it okay? Can you recall it from the book? Just let me know.
I
Should I
don't know if
open
it's okay.
it? Okay. Okay, now you can just recall this from the book also. Fetch decode execute. Now this is just the same process but written in a different manner. PC contains the address of the memory location of the next instruction. Be very, very careful. The word next instruction is very, very important when we talk about the PC, program counter. So program counter is containing the address of the next instruction being like the next instruction from the memory to be fetched from the memory. and then it is MAR. From PC, it goes to MAR. Now, this is what is the next stage. From PC, the data is moved to MAR using the address bus. Now, let me the word address bus is important that you need to know. The word, okay, now, address bus is copied from PC to MAR using the address bus. Again, the use of address bus is important here. Contents of the memory location contained in MAR are copied to MDR. Contents of MDR are then copied to CIR, and PC is incremented by 1. So then next instruction will be processed. Now just let me just make it simpler for you. If I just put it in the same order as is written here, first thing is PC is holding the address of the next instruction. I hope that that is clear.
Yeah.
Holds address of the next instruction. This is something very, very important. And just remember the keyword next instruction. Very, very important. If you're not mentioning the word next instruction, then that might result in you losing your mark completely. From PC, it's moved to MAR. So just making a shortcut for this whole process. Then from MAR, it moves to MDR, memory data register. And then we are mentioning just for our own convenience. And then from this, it moves to CIR, current instruction register, and that is your MDR, and then you can mention the PC is increased by 1. PC equals to PC plus 1. So the whole process that is done here is explained in the form of these to make you understand that this is what is the process. First of all, PC is holding the data, the address of the next instruction. From PC, it's copied to MAR as is mentioned here. From MAR, it moves to MDR as is mentioned here. The contents of the, and remember, MDR is holding the contents or the data or the value. So any of the word that is being mentioned in the paper, that means they're talking about MDR. Whether they say contents, whether they say value, whether they say anything like that, that is mentioning something similar, then you will take it as your MDR. Okay, got it? Same thing
Yeah.
that is mentioned here is shown with the help of the just simple thing for you to remember. And one more thing that you can see from here, very, very interesting. First at PC, in the next stage, PC is on the right-hand side and MAR is on the left-hand side. Then next stage, MAR is on the left-hand side and MDR is on the right-hand side. So in this manner, if you've actually understood the sequence of this, then the fetch decode execute will become very easy for you. In the decode state, the instruction is now decoded so that it can be interpreted in the next part of the cycle. And lastly, it's execution, where the CPU is going to pass the decode instruction as a set of control signals to appropriate computer components. Now be clear, after decoding, the CPU will be sending the signals to the appropriate components. Which component is supposed to be addressed? And that is done through the control signals. And control signals are somewhat assuming them to be just a sort of an alert signal telling that this is how the work is supposed to be done. And then the instructions will be followed in a logical sequence. And that is what will be completing your complete fetch decode execute cycle. Any questions?
No, it's good.
Okay. Now moving to cores, cache, and internal clock. So basically what are cores? Again, a question can come in the paper. You need to know the definition. We have talked about clock cycle that is there to synchronize all operations in the computer. Timing signals are generated and transmitted through the control bus, and increasing the increasing the clock speed might result in overclocking, but it may result in improving the performance. Like for example, near the exam, we can overclock. That's okay. But if I do the same system clock cycles performance a little faster during the normal routine classes, then maybe the students will not be able to understand. So similarly, in a computer, it may happen that your system will be able to adapt to the changing of the clock speed, but we need to be very cautious. If it's not resulting in the right results, then we have to revert back to our original one. Second thing, now just be clear, this is the first component that we have talked about. The first one is the system clock, the very first one. System clock is going to help in increasing, or you can say decreasing, the system performance. Second is the width of the address bus and the control bus. So a question can come in any style. That is why constantly talking about the only two buses, address bus and data bus, that are supposed to be increased to improve the system performance. As you can see here, A bus of 16 bits can address these locations, while if it's a 64-bit bus, that you can see it can actually almost handle this huge number of memory locations. So think from this perspective, although you don't need to know these values like 65536 or whatever, at least you can remember if it's 16-bit bus, it means it can address 2 to the power 16 locations. And if it's a 64-bit bus, it can hold or it can access 62 to the power 64 memory locations. So that makes sense?
Yeah.
Okay. First component, system clock, increasing, decreasing. Second factor is width of the address bus or the data bus. And third component is overclocking. And then you can see the same is re-mentioned, is again mentioned here. Causes by changing the clock speed in the basic input output system, or that is BIOS, that we are going to again discuss in chapter number 4 also, can lead to overheating and to non-synchronized operations. Cache. What is cache? Cache is holding the frequently used instructions. Like just think from our perspective. Assume that I am preparing maybe for a few things. Maybe the paper is tomorrow. So definitely, if the paper is tomorrow, my memory will be holding only tomorrow's paper data. Maybe it's some other paper which is going to be next week. I might be remembering, but I'll not be concentrating on that paper right now. So similarly, cache is just holding the frequently used instructions and data also. And this is going to help in speeding up the process. So when anything is stored in cache or when anything is stored in your frequently used instructions location, then the system performance will definitely be increased. The larger the cache memory size, the better the CPU performance is going to be. That is this third factor. And fourthly, it is core. And what is a core? Let me talk about that one. Factor number 4 is core. And factor number 4, core, is what is the definition? It's made up of ALU, CU, and registers. So you can assume this core to be a complete CPU. Okay. And then you need to
Yep.
know a quad core and a dual core. A quad core, as the name implies, means 4 cores are working together, or you can say 4 minds are working together. And a dual core means 2 minds or two cores are working together. So definitely from a normal core, if you're moving it to a dual core, you are assuming that at least the speed will be improved, although not entirely, it will be doubled. Same case goes for a quad core also, although we are assuming that if it's 8 cores, then it will be working like 4 times, but that will not be the actual case. There will be something less is going to be there, but that is substantial enough to help in improving the system performance. Okay, fine. So the
Yeah.
definition of core is clear. So from here, we have talked about the factors, and along with that, we have also talked about the terms that we need to know, like system clock, similarly cache, similarly core. They're coming in the paper quite frequently. An FDE cycle, a very important thing. So buses, registers are supposed to be understood and remembered by us. Now, then we have to know what is an instruction set. And do not confuse this instruction set with the character set that we have learned in chapter 1, ASCII and Unicode. What is an instruction set? See, instruction set are the operations that will be understood by that particular computer architecture. And this instruction set is made up of an opcode and an operand. So just think from this definition. The question can come in the paper. Like again, opcode informs the CPU what to do, what operations need to be done. Just like the action, just like the verb. An operand is the data which needs to be acted on, or it refers to the registers in the memory. So if I say, just giving an example, if I say run, run is going to be opcode because you are instructing or you are telling what to do, what is supposed to be done. And if I say anything like dealing with where to do, what is the data that is supposed, maybe if I say run 5 miles, or if I say run run for 50 minutes, for example. So that will be considered to be a sort of an operand, the data which needs to be acted on or refers to the registers. So since we are talking about the computer, that's why we are saying here that it is referring to the registers in the memory. Are we clear about this opcode and operand?
Yeah.
Now, this is the definition, and do not please be confused with the two terms. Instruction set is different and character set is different. A number of allowed opcodes exist, and these are referred to as the instruction set. So whatever your processor can comprehend, can work on, are the allowed opcodes. They are making an instruction set. And remember, every single architecture has a different instruction set. And these are simply the low level instructions which are understood by that CPU only. Like every architecture is designed differently. Similarly, the instruction sets are going to vary from processor to processor. So that is what we should be very clear about. Any questions? Because they will be telling the computer system or the CPU how to perform different activity. So that is why the instruction set may be different for different, the way instruction set is different for different people. Like talking about just an example, I have two students. One is told in a simple style and he is able to comprehend and work. It means his instruction set is simple one. Another student needs constant reminders to complete the work. It means his instruction set is different. Same case goes with the computer systems also. Okay, fine. To carry out an operation, the instruction sets may vary, and we need to know about this in order to work. Any questions?
That was good.
Okay. Embedded system, again, a very important topic from the examination point of view. What is it? A combination of hardware and software designed to carry out a specific task. Now remember, a dedicated task. Like embedded systems are just designed to perform one special task or one specific task or one dedicated task. Hardware can be electronic, electrical, or electromechanical. Embedded systems can be based on a microcontroller, microprocessor, or a system on chip, SoC. So this was just this brief discussion of what an embedded system is. A combination of hardware and software designed to carry out a specific task. It is based on microprocessor. You can talk about this one, and that will very safely give you 2 out of 2. Very easily, you will gain 2 out of 2. Got it?
Yeah.
Now, what is embedded system of a microcontroller? Made up of a CPU with RAM, ROM, and peripherals all embedded on a single chip. Now, what are peripherals? Peripherals are simply the components connected to the CPU. Under the control of CPU, they are called your peripherals. Are embedded on a single chip to carry out a specific task. Talking about microprocessor integrated circuit, as we started our lesson with, consisting of CPU only, no peripherals. And system on chip is containing a microcontroller as one of its components, and it usually includes a CPU, memory, input output, and secondary storage, all on a single chip. So this is what the whole thing is, but for this you need to simply know this one, and you will be gaining very decently 2 out of 2. Just definition and talking about a specific task, talking about the use of microprocessor, that will give you a very decent one. What is it composed of? It's composed of analog or digital input. A software is there to handle the hardware. Software and hardware is going to work on the embedded system. It can contain sensor input, mechanical components, actuators, and software. It can be getting modern systems using dual and quad core and a variety of I/O connections, and then they're going to give you the outcome or the output. Now, talking about the applications, where are they being used and the benefits? Another thing is embedded systems can be programmable or when installed, either the operator inputs data manually, for example, pressing a button or turning a knob to select a temperature, or automatically, for example, reading from a sensor. So again, there are two types of embedded systems. One is automatic, just based on sensor inputs, and another one is waiting for the input from the user. Embedded systems can be programmable or non-programmable. There are definite benefits and drawbacks, and from here, again, a question can come in the paper. Like the way we have talked about, a question can be asked. Part A is define embedded system, and part B can say write two benefits. Part C can say write two drawbacks. Small in size and therefore easy to fit. Compared to other systems, they are relatively low cost to make. So now, again, let me highlight the keywords so we can just concentrate. Small in size and therefore easy to fit. This is an advantage. Then second one is relatively low cost to make. And then dedicated to one task, making them simple interfaces and often no requirement of an operating system. Often they do not need an OS at all. So they are designed to do one task, so means they are simpler. Can consume very little power. Another advantage of them. Then you can say they can be controlled remotely using a mobile phone, for example, and controlled from a remote location. As you can see, a lot of applications are handled from a remote location. Very fast reaction to changing input also. So they're able to respond very quickly. And what are the drawbacks? Let's talk about the drawbacks also, and let's highlight the drawbacks also. Highlight them. Difficult to upgrade, and some devices but difficult to upgrade. Like once you have the embedded system, it is very difficult to upgrade them. Troubleshooting is difficult or a special task. Basically, troubleshooting is a specialized task, not done by everyone. Interface can appear to be simple, such as single knob. In reality, it can be more confusing. For example, changing the time on a cooker clock can require several steps. Maybe it is not convenient for some people. Some people are not tech savvy people, so that might be a little sort of I can say some problem for them. Any device that can be accessed over the internet is always open to hackers or viruses. So we cannot stay away from hackers or viruses at all. Due to the difficulty in upgrading, and fault finding, devices are often just thrown away. Like if anything is not as per my requirement, I'll simply throw it away. And that is resulting in a lot of problems that are occurring nowadays. So you can see they are increasing the carbon footprint. So they are becoming wasteful, can lead to environmental issues created by increase of the throwaway society, because we are increasing the process of just throwing it away, and that is increasing the carbon footprint. So that is just the benefits. And lastly, it's talking about the applications. You can see security systems, vending machines, washing machines, motor vehicles, everywhere you can see. And then the sample question and answers. And then here we can see that they've mentioned that why this question is good answer, very, very well answered, and why the question is not very well answered. Okay, fine. So inshallah,
Yeah.
fine. So just